one, or do we not?
I believe so. It was in the diagram where you, no, I was late, but I saw it on the board where you had the arrows pointing in the direction of the current.
All right, so current's flowing this way, and the electrons are flowing that way. And probably mentioned before, some textbooks will talk about electron current, and that's just the direction the electrons flow. I'm not too fond of that, but if you see electron current, that's opposite the direction of what those textbooks would call traditional current, or what I will call current. So I have current flowing in this wire right here. Current is flowing this way, but electrons are flowing this way. Now the electrons don't actually travel in a straight path, unless we got some superconducting going on, then it's really fun. But an electron's going to move along, it's going to hit something, bounce, hit, bounce, it's going to hit things, and it's going to bounce as it goes. So even though the electron's not traveling straight, it does have a tendency, if it's hooked to the battery, if there's a difference in potential, the electron does have a tendency to be moving in a particular direction at some drift speed, which we'll label as Vd.
We didn't have drift speed in 152.
Say it again?
We didn't have drift speed in 152. Now we have drift speed.
I thought we did have drift speed 152. But if not, it was just to confuse you and mess with your head. That is not never going to work. Now, the amount of charge that's going to be passing through, let's say that I have n electrons passing through that particular point in a certain amount of time, I basically have a current is equal to n times the electrons. So, number of electrons flowing. Actually, since current is charge over time, this actually should be just the charge of an electron. Now, yes, I've dropped the negative sign. I'm not worried about that. Now, the number of electrons that can actually flow depends upon the material. So I'm going to define lowercase n to be the charge carrier density. So it's not all the electrons, because not every electron is available to flow. It's only those that have enough energy to not be bound by a particular atom. So the charge carrier are the ones that actually can float. Actually, it should be mobile charge carrier.
So the mobile charge carrier density is the density of the charges that will actually move?
Yeah. Or are available to move. And so charge carrier density would be the number of charge carriers divided per volume. And so N would be the charge carrier density times volume. So the charge that's flowing, therefore, is going to be that mobile charge carrier density times the volume of charge times the actual charge of an electron per unit time. So we're dealing with how many charges can be flowing through this particular area. So in a particular amount of time, I'm going to have a certain number of charges flowing through here. Statistically, any one electron is just as likely to go through as another. So if I look at the volume here, so this is the volume of charge, volume of wire, in which with n time t, total charge of Q passes through. If I treat the wire, I always pictured it as a cylinder, but I guess I don't really need to. And if I picture that I have some cross-sectional area here, the distance that travel here is going to be my drift speed times time. And so my volume is just my cross-sectional area times my drift speed times time. That's the charge. Time goes away. And so I've simplified my current down to the charge carrier density, cross-sectional area of the wire, drift speed, charge of an electron. The magnitude of the charge of an electron. So we need to figure out what drift speed is. Or at least the average drift speed. I know that the charges are going to hit something and then bounce. It's just as likely to hit something here and bounce that way as it hits something and comes back, hits something here, and then bounces that way. So my drift speed, well, if acceleration is constant, I got a whole set of equations I can immediately jump into. Is acceleration constant? In between hitting things.
In between hitting?
In between hitting things.
In between hitting things.
So we would be looking at it only in the times in which it is not hitting things.
Correct.
I see.
So, in between hitting things, well, if I got a battery here, the high side and the low side, positive, negative side of the battery is producing an electric field traveling through the wire, and it is reasonable to assume that my electric field is relatively constant along any part of the wire. And if not, we're going to make that assumption anyway. So if the electric field is constant, then the force on the charges will be constant, therefore the acceleration is constant, therefore we can use the Cake formulas.
Yeah, the easy one.
If on average, my initial velocity is 0, because again, it's gonna hit something, stop, and then start moving, or it's gonna hit something going this way, stop, bounce off, and come back through. So if that on average is 0, then my drift speed is just gonna be acceleration times time, and my acceleration is going to be forced by my mass. And the force is just going to be the charge of the electron times my electric field over mass times time. And so popping it in over there, we get in my current in a little e, big E over mt times little e. Oh, I do have to make one small adjustment here. By leaving this time here as sort of generic, it makes it seem like that potentially a charge is gonna, I could pick any time and figure out how fast it's going, when in reality, we're looking at the times between colliding into things. So this t here really should be sort of an average time between collisions. So mean free time. It's material dependent, depends on how tightly packed it is, how many free electrons they have, etc. Actually, how packed it is. So I'm going to rearrange this into things that really are dependent upon the material and things that are not. So n, little n is dependent upon the material. Tau is dependent upon the material. A, the area, cross-sectional area of the wire, is dependent upon the wire itself. E squared over M is dependent upon the charge carrier, which we're assuming is an electron right now. And I'm left with the electric field, which is dependent upon some external source. If I bring constants together here, so I have this as N tau E squared over M, so this is the material dependent stuff plus the electron or charge carrier dependent stuff. This whole bit right here is just some constant, if we can make this correct assumption. If we are correct in assuming that it's the electrons flowing, times cross-sectional area of the wire times Y electric field.
Which is the same as the electric flux?
No.
Oh no, that's never mind, that's the top product.
Yeah. Just throw an electric flux in that. We generally don't see electric flux thrown into this. This whole bit here, if I know the material and I know the charge carrier, I know what's going to happen. I can figure out what this is, and so this is generally lumped into material specific constant, which they generally use the letter sigma for, and this sigma is known as conductivity. Take a quick look to make sure that I didn't leave something off.
Not to be confused with the other sigma for surface charge density.
That is correct.
Low.
We've run out of letters. So conductivity is a measure. If I have a material, the larger the value it is, the easier it is for charges to flow.
Is related to resistance?
It is. We're getting there. Now it turns out that sometimes we don't want to look at the conductivity. We want to look at how hard it is for something to move through. And so they did the clever maneuver of saying, well, if this is a measure of, if the larger this is, the easier it is for things to flow, then I want something that the smaller it is, the harder it is. Something which is the larger it is, the harder it is to flow. So they said, well, why don't we just take the reciprocal of it? And that is the resistivity.
And that rho, not to be confused with
The current density or other densities rho. That is correct. How many Greek letters start with a r sound? You got rho. And that doesn't explain sigma for conductivity. Right? So if I took that, then I've now reduced this to AE over rho. Now I need to somehow relate my electric field to, instead of I have a battery hooked up to a circuit, I'm not going to look at that and go, oh, the electric field is clearly. No, if I've got a power supply here, I know what the voltage is. So I need to connect E to my voltage. Well, I know that the change in potential, or my voltage, is the negative integral of E dot dr. If my electric field is constant, that just pops right out, so I get negative E dot integral of dr. And in essence, if I think about the length of the wire, R is going to go from some zero length to however long the wire is. Working under, again, the simplification that the electric field is parallel, or is running along the lines here of whatever the wire is. I have this relationship. It's the constant electric field relationship between voltage and electric field. So this now becomes A, bring the L over delta V over L rho. And yeah, I ignored the negative sign. Solving for delta V, because that's the more traditional form of it, I get I times rho L over A, which should look familiar to some of you. Well, actually, all of you are. This, we have resistivity which is a material-specific constant talking about how hard it is to flow. L, the longer it is, even harder it is to flow, it's more likely to hit things. But as the cross-sectional area increases, I got more room to move, so that would decrease this value. If A gets bigger, the value decreases, but this is what is called resistance. And so we end up with the voltage is equal to the current times the resistance.
There it is.
This is known as Ohm's law. Now, I don't know if Ohm was the first person to derive it, or whether Ohm came up with this experimentally, and then later they figured out how to derive it. But at the heart of it, this is not a new physics equation. This is just Coulomb's law. The only difference between this and Coulomb's law is math and definitions. We still have only worked with one physics equation, and everything else is manipulation of that.
Got it, 252. And then the memory serves resistivities, units are ohms.
Resistance units are ohms.
Okay.
All right, so let's talk about the units.
What's the difference between resistivity and impedance? They both use ohms, no?
Well, all right, let's talk about units. And of course, the erasers are getting together and plotting. So starting with Ohm's law, delta V equals IR. I know the units of delta V must equal the units of I times the units of R. If it's true, if Ohm's law is valid, which it really seems to be, this should be true. Let's stick with SI units for right now. Units of voltage,
Or
Volts.
units of current,
Coulombs per second.
coulombs per second. If we go back to that current is charge over time, then the units of charge, or units of current are the units of charge over the units of time, which is a coulomb per second. Now, as you know, coulombs per second, so much to write. So they came up with a shorthand, a one-word coulomb per second is known as Valerio,
Amps.
or more formally, amperes.
And you don't like the word amperage?
I do not like the word amperage. The word is current.
Got it.
Well, we must say amperage.
I'm fine with amps as a unit, I'm fine with amperes as a unit. Just the term amperage, current, fewer syllables, easier to say. And, yeah, there's certain words that you just shouldn't use. Amperage, utilize, cleaning.
Wait, what was the last one?
Cleaning one? Sorry, I've said it twice now.
Cleaning woman? What?
The words for, instead of amperage, use current. Instead of utilize, use the word use.
Yeah.
And instead of the word that you just said, you should use Heinemakaflau. If you have not seen Dead Men Don't Wear Plaid, I highly recommend it, and it would explain why you should use Heinemakaflau instead. So far, no one has managed to work it into anything yet.
Into a sentence.
Into actual, like, an assignment that's being handed in.
Oh.
Okay, so the units of current are amperes, coulombs per second also works. And so that times units of R. So the units of resistance would be a volt per ampere, which of course is way too much to write. And that is the ohm.
It's got a more symbol, capital.
It is a capital Omega. choice. It's a repeat of, for those who play word games. There is another unit, which is the reciprocal of the ohm. So if I have ohm to the -1, the symbol, you can legitimately do upside down capital Omega. And it is called oh. It is a legitimate word that use it to describe.
And all they did was take ohm backwards, huh?
Yep.
Flip the sign.
So are all the Greek letters used already? Or like, do they all have like a definition?
For the most part, the particles that, the symbols that are not used for units or standard variables are often symbols for particles themselves. Even though mu is one that could stand for micron, it could stand for permeability, it could stand for coefficient of friction, or it could stand for muon.
So some of them have like multiple, definitions or?
Oh, yeah, based on context.
Yeah.
With Greek and our alphabets, Roman, what is our alphabet called?
American alphabet.
Latin.
American.
All right, well, the American alphabet and Greek alphabet, upper and lowercase, we have 100 characters.
Oh, okay.
So we ran out. We had to repeat.
Yes, it's the Latin.
There's one other, just for the Scrabble players in the group. Later on, when we get to inductance, it will be in the units of Henrys. Henry. The reciprocal unit. It is a legitimate Scrabble word.
Yet again.
Brunette.
I have managed to use it once, which brought up the question of, what is that? Just make sure if you're gonna use those words, you have a dictionary that is sufficient to actually have it in there.